wrap up today. And we're going to go through system initialization to explain how the OS is loaded and initialized. Although if you have read Linux code, you might already have learned about it. And then we're going to talk about multi-core OS and the challenges. That hopefully we'll be able to finish that. That will be our main content today. And then next lecture, we'll talk about UI and how the graphical user interface and the command line user interface. And so there's typically a week before the exam week, which there's no lecture. Do other courses have lectures at in the last week? I remember there's a dead week or something. Is it?
Some do, some don't. It's just required that like homework during that week.
Homeworks, okay. Okay, yeah, we'll see. I think probably we'll try to finish the lecture content, at least the main lecture content that will be in the exam before the that week, so that you can do reviews. And so we may have some content, or we might have lecture during the dead week, but it might just be talking about the future trend and like how to do formal verification, like how to use AI and for system development and so on. Okay, so the last week, if we have any content, any lecture, the content won't be in the exam, but we'll see. I will try to wrap up everything before the dead week. Okay, all right. So, file system. So we talked about Linux file system implementation in the previous lecture, and I think, let me see which is right. So I think this. This might still be the best diagram that we can use to explain how Linux file system works. In Linux file system, if you remember, at any point in time, for each file, there is only one index block and one data block that is stored in memory. Okay. So Linux file system allows you to read from this specific data block or write to this specific data block. Okay, so we just want to do a quick recap, right? So this is the representation of one file in Linux file system. It has a list of index blocks, right? That each index block has the indexes to a set of an array of you can think of it as a linked list of data blocks. Okay. The first data block here is the first contains the first piece of data content for this file. This first is the first block. And the second data block, third data block, these data blocks contain the file content of this file. And the index block has indexes to these data blocks. Okay. And in the directory, you have a directory entry, which is the file name mapping to the pointer or the index to the first index block of this file. Right. And at any point in time, the Linux file system has one index block and one data block for a file. Right. What does that mean? So we can give an example. Right. So when you open a file, what happens? Right, so suppose this file is never loaded. Anyone remembers when you open a file, like what happens? Using this diagram, you can try to give my explanation. The file is never opened. When you open a file, what happens? roughly follow this diagram. Okay, if you remember, or you can take a guess, right? So just from the structure of this diagram, what happens when Xenu reads a file, open a file for the first time? How does it open this file?
Perhaps it matches the file name in the directory that traverses the index block, the data block, and copy that somewhere.
Yeah, that's correct, right? So remember this, in Xenu you have one directory block that's located at the top, right, at the beginning of the disk. So this is hard-coded. So Xenu knows where the directory block is. It will go to the directory block. If the directory block is not even loaded in memory, right? The file system was just initialized, right? If the directory block was not even loaded in memory, it will first load the directory block. Load the directory block to memory and search in this directory block where is this file, right? Using a file name. We'll find the file name and using the file name, it will find the first index block belonging to this file. And then what's next? Using this index, you know on the disk what's the location of this first index block. Right? So it will be able to load this index block from disk to memory. And then it will load the using the, because it just opened the file, so we can load the first data block belonging to this file, or you can delete it, right? So it doesn't have to load it the data block unless if you really need to read it. Okay, yeah, can if you want to read the first data block, you will use the first index in the index block to find the data block on disk and load it into memory. Okay, that's one question. Okay, now imagine when we read. So suppose we read this data block and we read past the offset or the boundary of the first data block. What happens? We went through this process in detail, right? So, but I hope that you're not remembering those details line by line, but you have a more high level, conceptual level understanding of what happens in these different scenarios. Sorry. And so what happens when you read past the first data block? Yes?
You have to check to see if it's in the same index block, and if it is, then just read the next data block in, and if it's not, then you need to read the next index block in and the next data block in.
Exactly, right? That's even one step beyond what I asked. That's very good, very good. Okay, so we will read this data block, read beyond its offset, right? Its boundary. You go to the index block to get the next index, next data block's index. In this case, we're assuming that suppose you're still in the same index block, you're just getting the next data block's index. And you use that to load this data block from disk. But before that, you also need to do an extra check whether the previous data block is dirty or not, whether you have written to it or not. If you have written to this data block, you need to write it back to disk before you load the next data block. Okay, so that's how what happens when Xenu reads beyond the current data block. And then the other scenario is, okay, I was reading the last data block in the first index block. So when I want to read the next data block, I need to go beyond the current index block. And that's a different scenario. Then I need to put that, if that index block is dirty, we need to write it back. If not, I can just go ahead and load the next index block. After I load the next index block, then I can find the first index in this second index block and continue reading. Okay. So there are a few different edge cases during the execution of reading a file or writing a file in the file system. But they can all be illustrated using this diagram. So if you understand how the file system works at high level, you will be able to explain that just following this diagram. Okay. Right. We explained this, right? So you can see that this is the data structure Xenu uses for a file, and you can see that at any point in time, it has only one data block and one index block in memory. It's not holding multiple blocks for each file. Okay. And we also explained the read process, but we won't go into the detail. I think I pointed you guys to read this file, or this function, LF setup. This is the function that does the previous check, checking whether the read or write exceeds the current data block boundary, and whether it exceeds the current index block boundary, and handle them correctly. It's all handled in this LF setup function. All right. So Xenu makes a simplified design, right? So to not allow concurrent access to a shared file, right? So in the modern file system, you often see that you can allow multiple process to open one file and read it together, right? But in Xenu, to avoid this concurrent access, the Xenu local file system prevents concurrent access. Okay. These are not the most important thing. Right, so this is just a quick explanation that the index block is much smaller than data block. So on disk, in each disk block, it can store multiple index blocks. Right? In Xenu, there are 7 index blocks in each data block, in each disk block. Okay. This is index blocks definition. So I won't go through the details. This is how to read an index block, right? Find this index block on disk and load it from disk into memory, right? So right, you can read this function in detail after the class. Right, so this is how to write an index block back to disk. Okay, so that is the simplified file system Xenu implements. The Unix file system is more complicated than Xenu's file system, and the core is the tree-structured file system with inode as a central data structure. Right? We have explained it in detail, so we'll quickly go through the slides. Let me see, I remember. Yeah, so this is inode, right? So this diagram illustrates the inode data structure in Linux or Unix file system, and so we have explained it in the generic file system that lecture. So we won't really spend too much time on this. Let's just quickly go through the Unix file system. So the operating system maintains an open file table, and this open file table is internal to the OS and has one entry for each open file, and it uses a reference count that allows concurrent access. So this is a more general design compared to what Xenu has. Right? Remember, Xenu has a limited number of pseudo devices that you can use to for each file that you open. So the number of pseudo devices. Okay, and each process has a file descriptor table. Right? It has a array, and this array contains all the files that are opened by this process. Okay, and this each entry points to one entry in the open file table, right? Because this open file table can be shared by multiple processes. Okay, and every file has a file descriptor once it's open. Right? It's a small integer returned by open and provides the index into the process's file descriptor table, so it's only meaningful inside this specific process. Okay. Yeah. So the Unix file descriptor provides access to mechanisms other than local files. I can refer to IO device, network socket, remote file. So this is what we mean by everything is file philosophy in Unix. So in Unix operating system, everything can have a file descriptor, and you can use this file descriptor to perform file operations. Right? These file operations are open, write, read. Right? These operations, they are called file operations, but they are essentially treating the file and device as a sequence of bytes, as we explained. Although it's people see it's everything is file, it's really the truth is that everything is treated as a byte stream. And that is an easier way to understand it. If you see everything is a file, sometimes you might get confused. Why is everything a file? But if you see everything is a byte stream, because all the devices can be manipulated in this way, right? Sending a byte, receiving a byte. That's why everything can be modeled as a byte stream. Okay, and you can even I think there's an interesting type of tool that are invented in Unix. Pipe. I'm not sure whether you guys are familiar with it. Pipe, right? And it's very often used. Whenever you use a command line command, containing multiple command line commands together, you can redirect the output of the first command to the second. As an input to the second command, you are creating a pipe in between these commands. Right? This pipe data structure is actually a temporary byte stream or temporary device. Right? Essentially, you're creating a temporary byte stream. Right? So it bridges the output of the first command to the input of the second command. And that is a very elegant example of the philosophy of Unix. Right? Everything is a byte stream. Pipe is a byte stream that you can use to connect to other byte streams. Okay, and yeah. So if you have been working in Linux environment for a very long time, you know how powerful this pipe data structure, this pipe file tool is. Right? So you very often need to connect concatenate multiple commands together, and it's very powerful. Okay. Inheritance, right? You can inherit open file, and you can share open file and increase its reference count. We won't go into details of this. Right. So a Unix inode. We explained this in detail in our previous lecture. So we will just we'll just quickly show what inode is again. Yeah, using this diagram. So it has a direct blocks. Right? So in the very beginning, the start section of the inode, every pointer points to a direct data block, which is stores the content of the file. And then in the later part of the inode, it has indirect block. Right? Every indirect block points to a block that stores indexes to data blocks of the file. Okay? And then you have double indirect blocks and the triple indirect blocks. Okay? Every level of indirection you add, you are increasing the amount of the limit of the file size in your file system. Okay, right. You can see that if you don't have a direct indirect block, double indirect block or triple indirect block, those number of direct data blocks are the limit of the file size. Okay, and if you have an indirect block, you can see that it easily doubles the amount of blocks that you can have in a file. And if you have a double indirect, again, your file size grows exponentially. Every level of indirection you have, the file size limit grows exponentially. Okay. Yeah. So far, people really need a larger file than what can be provided by triple indirection. So that's why inodes in most modern operating system only have a triple indirection. Okay. So the benefit of this, I remember that we have the Xenos design is that everything is linked in the linked list. Right? So the I blocks are linked in the linked list, and the data blocks are also organized in the linked list. So this inode design has a benefit, right? So it allows you rapid access to small files. Right? Why? Because the inode has direct links to the data blocks. Right? For most of its data blocks, if the file is very small. You don't need to go through any level of indirection. For a small file, all of these blocks can be stored in those direct blocks. Okay, and for medium-sized files, you can have fairly rapid access, right? Because you only have one level of indirection, probably, and for large file size, you have a slower speed. That's the main thing that we want to cover, because here for caching, so there's a few slides on caching, but we did not really explain, the slides did not explain the detail of caching. So the page buffers, right, in Linux, you can see that there are page cache, page buffers that you can use to cache the content of the file. But here, in the slides, we did not explain the detail, so I won't cover it. Okay. So there are some questions that, if you're interested, you can think about it. That's file system. System initialization, right? So we have covered most functionalities of OS and how it's implemented in this class, but we did not mention how the OS gets started. So how many of you have read the startup, the bootstrap code in Xenu? Has any of you read? Some of you. Okay. And it's interesting to see, right? So how is OS started? Okay, so the idea is very simple. Right? So the OS need to be loaded into memory just like a normal program, right? So when you initialize your system, you need to figure out where to load OS program into memory. That is the high level idea, the task that you need to perform when you do system initialization. Identify the location of OS program on disk, load it into memory, run the setup that's needed, right? You initialize the variables, the configuration, and memory allocation, etc. Okay. But the first thing to do is to identify the location of OS on disk and load it. You can imagine in the very early days, the simplest way is to assume that the OS is always written to one predefined location on disk. Right? And your hardware, your machine's hardware can be wired or hard-coded so that it always goes to that location to load your operating system. Right? But that's just very inflexible, so that's why people have this small bootloader, right? Small bootstrap program that you can load into memory, and that bootloader, that bootstrap program will find the location of the OS and load the OS itself. After the OS is loaded, every module in the OS itself will get initialized by the OS, and that's a high level idea. But let's go through this process in more detail. Okay, so how do we start a computer from scratch? Right. So the general idea is that the OS is typically not the first piece of software that runs, unless you use the hard-coded approach, right? So you predefine the first section of disk is the OS, and your machine always goes to that location to load the OS. Okay. Yeah. So but typically OS is not the first piece of software. There is a hardware that performs some basic initialization when you power up your computer, and the CPU starts the fetch execute cycle, right? Remember, CPU is just a big cycle. Every time it fetches an instruction and executes an instruction, right? But before your OS is even loaded in memory, what is it fetching, right? The CPU, when you power up your computer, your CPU starts running this loop. Fetch, execute, fetch, execute. Your OS is not even loaded. What is it fetching and what is it executing? So there is a piece of code that is hard-coded in flash memory or ROM, right? So which is a special piece of hardware on your machine. So this software is predefined in its ROM, and it's not modified. Right? It's not going to be modified. It's most of the time it's shifted. It's shifted with your machine. Okay, that is the first piece of software that will start execute. Right? So the CPU is hard coded to start its fetch and execution cycle from the software stored in the ROM. Okay. All right. So this piece of software, it will perform some sanity checks on the hardware. Right? Check whether your memory is working correctly, whether your disk is working correctly, whether your CPU is working correctly, right? And do some sanity checks and some necessary hardware initialization. Okay, and this ROM code will identify a boot device and find an executable image and load a copy into memory. What is this? This is the OS. First, identifies a boot device, meaning that the device contains the OS. Okay, And this executable image is OS program, and loads is a copy of your OS program into memory. Okay. Right. And yeah, so the ROM code does some before it starts really executing the OS code. It also does some other initialization. Sets the hardware registers for kernel mode, because the OS typically starts in a special mode called kernel mode. And after the OS finishes its initialization, it will lift itself to user mode so that the user programs can run. But before that, it's in kernel mode. Okay, and the ROM code also sets the physical area space, and then after it finishes all of this execution, it will branch to the entry point of the image, which is your OS. This is when your OS really starts executing. Right. So the ROM code is the bootstrapper or bootloader. Okay, it does all of these initializations before it loads your OS into the memory and starts executing it. Okay. Yeah, if you're interested, read the bootloader in Xenu, right? So although it's written in assembly code, right, but it's not very complicated. Right? It's still relatively short, so you should be able to understand it. Okay. Oh, sorry. Sometimes the image itself is also split. Right? So after you loaded this image itself could be a small piece of software which later load your OS. Okay, this also happens. Right? So it's a bootstrap program that has the ability to identify some devices that contains code to use them, and it's configured with a set of devices to try. Right? So it can see a bunch of devices because OS might be stored. If you want your system to be more flexible, you want your OS to be stored on different devices. Right? So this bootloader can see multiple disks, right? And your OS is allowed to be stored on any of them. This is a more advanced version. In the very old days, we don't have this, right? So we just have the ROM that directly loads the OS. But after that, right, the modern system usually have this intermediate step where you can have this bootstrapper, and it allows you to put your OS on different devices. Okay, provides more flexibility. All right. So, yeah. This is an example strategy. The hard disk contains an executed image, then we'll load and run it. If an external USB drive contains a bootable image, load and run it. Right? So these are all the different places where you can put your OS. Okay. So this bootstrap program allows you to put your OS in multiple different hard disks, or even internal USB drive, or even over the network. Okay, so the bootstrap program has the ability to see these hardware devices and communicate with them. In comparison, the ROM program does not have this ability. Okay, all right. So yeah, because of this bootstrap program is able to load your OS from these different devices, and after the OS is loaded, that's when you really start the OS execution. Yeah, so this example shows the bootstrap complexity, right? So the bootstrap has many subtleties to
handle, but we won't go through this, right? So if you're interested, you can read it. The Linux bootstrap process is not that trivial, right? Because the OS is not stored locally. The Linux OS is stored over the network, right? You need network communication to load the OS. Okay. Yep. If you're interested, you can read this example in detail. Yep. So the solution. Right? We'll jump directly to the solution. In Linux, we have this bootstrap program called Xboot. Right? It is able to use standard network protocols, UDP over IP, to communicate over the network and read the Linux image from the network. Right? It can contact a server in the lab and use TFTP to download a file and place it in memory and branch to the entry point of the program. This is how it downloads the OS, the OS image. Okay. Yeah. So the tricky part here is that the bootstrap program itself need to be able to communicate with the network device. So it needs to be able to use the device driver for network device. Right? And it also need to contain the code to handle basic network protocols and a way to handle network packets asynchronously. Right? So this is why the bootstrap program itself is not small, right? Because it need to at least have the device drivers for these devices it communicate with. Right? Network, USB, hard drive, right? You need to have these device drivers. Okay. All right. So because we already have these necessary pieces in Linux, so Xboot is actually just a small, stripped version of Linux in which the main program performs the download. Right? It's just a Linux that only performs the download. Okay. Yeah. So some other questions, right? For example, where should a bootstrap program reside? Right? Where do we put it in memory? So the goal is to put an operating system, and the operating system itself starts at physical location 0. Right? If the OS need to take the memory address starting from address 0, where do we put the bootstrap program? Okay. Right? So if the bootstrap program uses location starting at 0, then the bootstrap will be overwritten when the operating system is loaded. Okay. So there are two approaches. One is self-replicating code. Right? The bootstrap is loaded into location starting at 0, and the code creates a copy of itself at a high memory, and then branches to the copy. Right? So in the beginning, it's loaded to the to address 0 in main memory, but once it starts executing, it will create itself in the high memory address. Okay. And once it branches to the copy, it will see that, okay, I'm in the high memory address, so I will not make another copy, right? So it cannot copy itself forever. Okay. And yeah, once it's made the copy, it will start execution. Right. So the first copy of it, which is loaded at starting at 0, can be safely overwritten by the operating system, which later will be loaded. The other approach, right? So the bootstrap compile the link to use addresses beyond the operating system. Right? It's directly loaded to it's placed in the memory at a link address. The bootstrap can load the operating system without overwriting the bootstrap code. Okay. So essentially, this address is linked to use addresses beyond the OS. It cannot use the address starting from 0. Okay. Yeah, so there are some tricky problems to solve, such as self-relocating code must change all the address constants, and this is a bit tricky to solve, and export use the second approach. So link the addresses beyond OS, and the OS will directly be loaded to address 0. Okay. So once the bootstrap problem finish its execution, the OS is itself is loaded to the beginning of memory, right, to address 0. And then that's when the OS really starts execution. Okay. So these are the steps and OS takes when it starts. Right? Let's go through this slowly. Right? So it's not very complicated, and conceptually it's doing very simple things. So it performs remaining initialization required by the hardware. Right? So there are some hardware initialization you need to do. Okay, and you initialize the memory management hardware and the free memory list. So this is to prepare for the memory management unit, so that the OS can really start allocating memory. Okay, and initialize each OS module. Right? In the OS, you have network module, you have memory management, you have file system. All of these modules will need their own initialization. Okay, so you initialize every OS module, and then after that, you can load and initialize device drivers for each device. Okay, so for disk device, network device. Okay, and yeah, clean up, right, reset each I/O device, make sure that they are clean, and then this is essentially done. Right? So initialize hardware, initialize memory management, and initialize every module. Right? So the file system, network module, all of these modules, and then initialize the device drivers. Okay, that's most of the things that need to be done when you start an OS. And then after that, you transform from a sequential program to a concurrent program. This step is an interesting step. Right? Because before this step, you can see that the OS itself is a sequential program. When you just start execution of the OS is just a sequential program. There's no other programs that are running on the machine. It's just one single sequential program getting executed by the CPU fetch and execute loop. And starting from address 0, the CPU fetch, okay, the first instruction from address 0, I'll execute it, and then I'll fetch the next instruction at address 1 and execute that instruction. That's how OS is executed before this step. It's just one big sequential program starting at memory address 0, and CPU is just executing it sequentially. Okay? But this is where you do the transformation. Because our OS is a multitasking, multi-programming OS which support multiple processes to run concurrently. How do we make that transformation? Right, this is the step that we transform from a sequential program to concurrent system. Okay, later we'll see. Yeah, we create a null process and then create a process to user code. So after this transformation, you can create multiple processes, and these processes will execute concurrently. Okay. So what happened in that step? We'll come back to this, but let's look at the more interesting. So how that transformation is done. Right, how to transform our sequential OS execution to a concurrent program system. So it is the most significant aspect of initialization, but at the conceptual level, because everything else is just initializing every component, right? Memory, file system, network, and so on, every component in the OS. It's conceptually it's very simple. But changing from one sequential program to concurrent program, this is sounds quite interesting, not very easy to do. So it is the most significant aspect of initialization, but the implementation, the solution is actually quite simple. Right? So it occurs in Xenu's function sysinit, right? If you are interested to read this function, and it's very simple and elegant. Right? It allows the fetch and execute cycle to continue, and it does not involve complicated changes like changing code or special instructions or using jump instruction to jump from a sequential program to a concurrent program. It does not do any of that. Right? So the idea in Xenu is that the code keeps running, but we just change the way that we view the system. Right? So the idea is this. Right? So first, we create a null process. Right? Now we fill in the process table entry for process 0. We create this null process and make the state current and priority 0. Right? What that is. So before this step, before we create this null process and setting null process state to current, conceptually there was no process running in the OS. And there was just the OS being loaded in, and the initialization function is initializing every component. But there was no process that's running before this step. Okay? When there's no process running, what's the consequence? Even if you have, I think before this step, we don't even turn on those timer interrupt. But you can imagine, before this step, even if you allow timer interrupt to happen, what's the consequence? It does not trigger anything. There's nothing in the process queue. Right? There's no process in the ready queue. Even if you allow the timer interrupt to happen, there's no process to schedule. So there's really no concurrent execution of any program. Right? So this is the step where we create the first process and set this process to current, meaning that this is the process that's currently executed, and now we have the first process, and then later we'll create a user program, put it in the ready list. That's when we transform the execution from a sequential execution to a concurrent multi-process execution. The reason is that before this step, although we have all the code, right? The OS, Xenu kernel has all the code for the process management. It has a scheduler, it has a ready queue, it has all of those. But before this step, there's nothing to schedule, no process to schedule. Even if timer interrupt happens, you will not switch between different processes. The program just executes sequentially following the initialization function. After this step, once we create this null process, that's when the system really turns into a concurrent OS. And even if we do not create the next the user program, even if we only have this null process itself in the OS, it's still a concurrent OS. The scheduler will be working, the timer will happen, and when timer interrupt happens, the scheduler will check, okay, there is no other available process in the ready queue, so it will continue executing the null process. That's still a version of concurrent program, concurrent OS. Okay, so this is the concept, how the OS transforms from a sequential program to a concurrent program. After we create the first process and set its execution state to be current and turn on the enable the timer interrupts, and that's when we turn our OS into a concurrent OS. Right. Yeah, so make the state current and make the priority 0. Set current PID to 0, meaning that the current process that's getting executed is this null process. Right? And this is all, right? This is how we turn the sequential OS into a concurrent system. Okay. So, oh yeah, sorry. You need to allocate the stack and fill in the process table entries for the stack. So these are all the initialization work that need to be done for the null process. Okay, so in essence, we declare the current program to be the null process. This is how we transform the OS into a concurrent system. Okay. Yeah. So after that, we can create and resume a user process for the user program or the main program, and then the OS can take over and schedule the main program to be executed. Right? After context switch, the null process will be swapped out, switched out, and the main program will be switched in and will be executed. Okay, yeah. So when resume is called, the magic happens. The reschedule choose a new process because the new process has higher priority. Right? The main program has higher priority than the null process, and the context switch will proceed as usual, and now you have a concurrent problem. Okay, so this is the interesting step in the system initialization. So this right, this is the interesting part. The previous part, these are just initializing every component of the OS. And so these slides like, initialize the processor hardware, initialize the bus, zero out the DSS segment, initialize co-processor if there is, create environment for C, and invoke C initializer function, and so these are all more standard initialization functions. So we also explain this. The sysinit function also initialize the memory management hardware and the free memory list, I/O device, the OS modules, and arrange for the current computation to be the null process, and then enable interrupts. So this is a step. This is a step that transformed the OS to a concurrent system, and then after that we enable interrupts. This is when the timer interrupt is able to interrupt the scheduler, and after that, if you add any problem, right, so you can start doing context switch. Okay. So to summarize the transformation. Does this, right? It fills in the process table entry for process 0 or the null process. And the code sets the variable current PID to 0, which indicates the current process being executed on the CPU. And this transforms the sequential program to the null process. Okay. Yeah. Startup involves many low-level hardware specific details. Right, so getting the startup code to work correctly is actually quite complicated. Right? And when the OS starts up, it runs a sequential program, and then instead of creating a separate concurrent system and jump to it, the code declares the null process is running and invokes create another process running the main function. And this turns the system to a concurrent system. Okay, that is system initialization. Right? So if there's one thing that you want to understand from the system initialization, that's how the system transformed from a sequential program to a concurrent system. The others are initialization details. If you're interested, you can read the code itself to understand. So the next topic we'll cover briefly, right? Not in a lot of detail, is multi-core operating system. So Xenu is designed, so the default setup that we're using in Xenu is a single core, right? But multi-core OS is the predominant type of setup that you will face in your own laptop and in a cloud system, right, in those big companies. Single core is still exists, but probably mostly in embedded systems. And of course, Xenu is an OS for embedded systems, so that's why it's suitable there. Right? So why it's a single core design is okay. But in the most modern system, operating system, you need to support multi-core. And supporting multi-core is very complicated. Okay. So a bit of a history on parallel computers. In the hardware world, parallelism provides a key to optimize performance. If you can run multiple executions in parallel, of course, you have you can double, triple your performance. Yeah, it has been used since early of computers, and for example, processors and I/O devices, they operate in parallel. Right? So that's why even in single core computer, you can do scheduling so that some process, when some process is using CPU, the other process can do I/O. Okay. And individual hardware components within a processor use parallelism to achieve higher speed. Okay. Yeah, in the architecture course or computer organization course, if you are taking that course, if you remember that every CPU, even if it's a single core, it has multiple stages, and it can. These stages form a pattern, and you can run multiple instructions, right, at the same time, because each of the in the CPU, because each of the instructions might only be working on one stage in the pipeline. That's another form of parallelism. Each stage in the CPU pipeline can work in parallel. That's how it allows multiple instructions to be executed on even a single core CPU. Okay. All right. Yeah. So in 1980s, there's parallel computers. Right? So the becomes a hot trend. Right? There are startups and major computer companies started building these parallel multiprocessors. Okay. The most popular form, symmetric multiprocessors. Right? So every processor, every core is equivalent. They are equal to each other. Right? So that's why it's called symmetric. It consists of multiple identical processors and an interconnected mechanism that allows them to communicate and share data. Okay, and the results in the very beginning are disappointing. Performance did not scale linearly. And the challenge is how the communicate and share data. Allow multiple computing units to share data efficiently is very, very difficult. Okay, so this takes years of research, decades of research to make the communication efficient. Okay, so in the 1990s, a number of transistors that could be placed on a chip had grown to billions. Right? So the hardware technique has improved, and the heat generated by high clock rates had become excessive, and instead of increasing clock rates, chip makers began introducing SMP on a single chip. Right? In a single CPU, you have multiple processors. Okay, so before this, in the 1980s, you have multiple independent processors. Now you have multiple processors on a single chip. Right? So yeah, to avoid being associated with the idea that few chip manufacturers invented the marketing term multi-core, but the idea is the same. You have multiple processors that share data. What makes this successful? What makes a multi-core successful than the previous parallel processor? Can you imagine? And because they are placed on the same chip, the communication becomes much faster. Okay, and then on the single chip, they also place the multiple layers of caches, right, to make sure that the data sharing and the communication is more efficient. So the difference is the cost of communication becomes much lower when they are placed on a single chip. Okay. All right. So multi-core, you have a single chip that contains multiple identical processors and an interconnection mechanism that allows them to communicate and share data. Still, the same thing. Their goal is to communicate and share data. Okay. You also have a way to start only one core when the chip boots, and then allow that core to start other cores as needed. But this is not the core concern, the major concern. Okay. In practice, core 0 usually differs slightly from others because core 0 need to boost it starts up when the system starts up, and it need to be responsible to start the other cores. Okay. Right. So this is the example architecture of a multi-core. Right. So you have core 0, core 1, core 2, and core n. And each core have their own local cache, and they could have this is a layer 1 cache, but in other modern multi-core CPU, you have layer 2 and layer 3 cache, and that's shared by multiple of them. Okay, and you can imagine that there is another shared cache that is below this local cache that's shared by all the cores. That's essentially L3 cache in modern CPUs. Okay, and in this chip, there are onboard bus inside the chip. These are very high-speed communication channels. Okay, and because these cores reside on the same chip, these onboard bus are very fast. Okay, and then you have external bus, right? So this is the chip, and this chip is connected with other devices, I/O devices, disk and memory, right, through the external bus. Yeah, I'm not sure nowadays do people still try to turn to disassemble your computer and look inside your computer what it looks like, right? But in the old days, I think when I was an undergraduate, we do that, right? So we tell our own computer apart, and we can look at the bus on the motherboard and also the keyboards. And nowadays, it might be more difficult. Right. So the onboard bus differs from the external bus. It should be much faster, and each core has its own L1 memory cache, and some design allows groups of cores to share L2 cache, right? So they could share one. All of them can share one large cache. Okay. All right. Yeah. So some manufacturers, they offer specialized communication mechanism that allows a core to send a message to another core, or allow a core to broadcast message to other cores. So you can send. The first one is point-to-point communication. The second one, broadcast, is a multicast or broadcast mechanism. So these these functionality could be provided in the hardware layer. Okay. And some other manufacturers use the interrupt-like mechanism that allows a core to interrupt another core. Okay. You can see one key challenge in this design is that every core has its local cache, but their cache share data. Right? You can imagine there might be one piece of data, some variable in the memory, and this shared variable is shared by multiple threads. And let's see, unfortunately, these two threads are scheduled to be executed on two different cores in your CPU. Right, these two threads share one variable, but these two threads are executed on two different cores. And you can imagine that their local cache, could have their own copy of this variable and this shared variable, and they need to make sure this shared variable is consistent between the caches. Right. Each core has their own cache. If they share some data, that data need to be consistent across these caches. This is a very difficult problem to solve, and over the years, there are decades of research studying cache coherence protocols, how to make sure that this data is consistent among the caches. Okay. So this is an explanation of the example. Right? Core 0 initialize a shared variable x to be 0, and core 1 access x and placing write a value 0 in its cache. Core 2, because it shares this variable, it also places a value 0 in its cache, but the core 1 increments x, writing 1 in memory, and core 2 access x and obtains 0 from its cache. Right. So in step 1, core 1 increments this variable to be 1, but the core 2 does not see it, because in its local cache, it still sees this old value, the stale value of x. Okay. So the coordination among these cores and their caches need to be implemented to make sure that this data is consistent among the caches. Okay. The simplest idea is whenever core 1 writes and shared variable x, they need to invalidate the corresponding cache lines in all the other caches on the same chip. Right? So it writes this variable variable x, and the variable x maybe stays in, let's say, the cache line 10, right, in this local cache, and this will cause the hardware to send an invalidation message, broadcast to all the other cores of the cache, and see that, okay, your cache line, right? So if your cache line 10 is invalidated, whatever data you had before is old data. You need to load the new data again, right? Because this variable value has been changed. Right? This is the simplest solution. It's not very efficient, and there are decades of research optimizing this strategy. But the core here is that when you have a write, you need to coordinate with other caches to invalidate their old value. Okay. All right. Yeah, I think we'll we'll explain this detail in our next lecture, and yeah, we'll continue with this in our next lecture. That's it for today. Thanks.